Welcome back. Let's complete our discussion about open cavity. First, we will continue how to run the program. First, let me show you the Muller's master to find the root. Okay, here is the Muller master. Actually, the best way is to perform the program and change the variable by yourself. You will have better understanding. So the program tests to solve the roots of f of x, s squared plus 1 equals 0. And then we use the Muller and substitute everything to get the result. And eventually, we got the solution. Of course, it's plus and positive and negative I. Okay? And function C root, CF is shown here, allow us to calculate. Okay, that's the final result. Muller can be found in many textbooks. Okay, so you can study by yourself. Runge-Kutta integration. Okay, here is an example. If you want to solve this one and this equation, such as with the initial condition here, and integrate from the left to the right, then you can perform the integration just like this one. Runge-Kutta. Write a short program, easy to understand, easy to control all the parameters. If the complete program is not easy to understand, then you can separate them into several parts. Understand each part step by step will be very helpful. Now you have the idea of Runge-Kutta, Muller and Runge-Kutta. Now let's enter spectral domain analysis of open cavities. We just talked about time domain. Then go back to spectral domain, frequency domain. Different viewpoint. Time domain, frequency domain looks like Fourier transform and inverse Fourier transform. The reason co-tests of open cavity almost always employ the method of frequency sweeping. When we test an open cavity, we always inject a signal and change the frequency step by step, one frequency at a time. And Q value is measured by its spectral domain definition, hence denoted by a subscript omega, where delta omega change the frequency superscript omega. The full width between the half hexima and the resonance line quality factor of the cavity time domain is defined here. However, frequency domain, we have a superscript omega, superscript T for time domain, superscript omega for frequency domain. And here is different. Omega 0, central frequency, resonance frequency divided by delta omega is the full width between the half maxima, 半高宽. Okay. They should be slightly different, quite similar, but different slightly. Okay. Numerical approaches for the spectral domain, we also make 3 assumptions. Time domain, we use this structure. Frequency domain, you can use a slightly different structure. We use the incident wave from here, and they were partially transmitted into the here and partially reflected. And we assume a reflection coefficient here. Okay, so it should be partially incident wave and will be partially reflected. So reflection coefficient is always exist. Okay, so we measure gamma, the frequency response of gamma. Frequency domain, complex reflection coefficient, gamma. Okay. One frequency at a time. Numerical model is slightly different with a proper guess of the value gamma. And we then put FZ1, we got this one, FZ1 prime. F prime of Z1 is shown here. Since F is given at Z equals G1, F prime is also set accordingly. Okay? Once we know this one. Integration from Z1 to Z5 using Runge-Kutta method. We also use Runge-Kutta and check the boundary condition at Z5 using the Muller's method to guess the next root for gamma, reflection coefficient gamma. Gamma is a complex. Keep this in mind. Iterative integrations, each time with an improved guess of omega. For gamma here, the typo gamma will eventually converge to a correct solution for gamma. And f of z will satisfy all the boundary conditions. Our purpose is to find gamma. So go back to here. We integrate from Z1. Z1 is given with the incident wave and guess a reflected wave and check the boundary condition at here. And we will find another gamma. Frequency is given here, one frequency at a time. And here is automatically found a resonance frequency. So these two approach is different. This is gamma, this is gamma. Okay, some typo. And frequency response, as we change the frequency with the normalized with respect to the cutoff frequency. Cutoff frequency should be here. Okay, the field amplitude squared is shown here. L equal 1, L equal 2, L equal 3, L equal 4. Okay, let's calculate maximum field spectrum for TE11L modes. Calculate the result. And theta is the taper angle. Others are the same. Okay, numerical results. Numerical result obtained under the temporal time domain and spectral domains for the cavity dimension in table 1 with different output taper angle theta. The TE11L will calculate FC is the cutoff frequency of the main body of the cavity. Okay, change this one. And for 1, 2, 3, L equal 1, 2, 3, and this is the frequency, time domain resonance frequency, for spectral domain frequency obtained by sweeping the frequency. Quite similar, but differ slightly. Okay, and we use this software. So we use a cavity like this one. An example. Let me give you two examples. First example is frequency tunable terahertz gyratron at 394 gigahertz using open cavity structure. Okay, this is the cavity. Two taper. It's not a sharp cutoff, but a taper and another taper. So first axial mode, second axial mode, third axial mode, and we obtained it. First axial mode resonance frequency very high. Second axial mode, third axial mode. Q1 is shown here. Okay, frequency tunability. L equal 1, L equal 2. Okay, we just using the open cavity structure to calculate everything. This paper was published in Journal of Applied Physics, frequency tunable gyrotron using backward wave components with high citation. Second, another example. We change to this structure is a sharp cutoff, but in the middle is not uniform, but also taper, 4 taper section. So middle section is not uniform at all. It's an ongoing interaction, ongoing research with Fukui University. So as you can see here, that's for velocity spread. This structure is good for uniform, for high power at 200 gigahertz, and also with high citation. Dr. Cheng, because of this work, Dr. Cheng received an invited talk for International Conference on microwave, millimeter wave, and terahertz wave. So finally, thank you very much for your attention. That's all for today. Bye-bye. See you next time.